Hello, and welcome to the PyHPC workshop keynote address. My name is Mike Bauer. I'm a research scientist at NVIDIA Research, and today I'll be talking about reprising the Zen of Python for high-performance computing. Before I dive into that, I want to start with a very brief confessional. I'm a PyHPC outsider. I'm relatively new to the community. I've been using Python for about 15 years, but only for about the past 3 for doing high-performance computing. I don't necessarily think that's a bad thing. I think it reflects the fact that, I'm by being relatively new, I'm actually going to be able to offer hopefully some interesting insights that you'll appreciate. And so, all in that regards, first I'd like to sort of congratulate the community. I found it really to be a breath of fresh air. I find the community very open to change and trying new ideas and experimenting and exploring new program systems, and it's really refreshing to me to encounter that, and I've very much enjoyed it. And so I wanted to compliment the community at large about that fact. That being said, I'm often routinely underwhelmed by how unPythonic a lot of the code that I find in the PyHPC community is. Python really has a very strong ethos of writing Pythonic code, and we're going to define what that means. And oftentimes I find that we often trade off performance a little too much sometimes when we actually go to write that code. And so what I want to do in this talk is to actually examine why that's the case, what impacts it's having, both in our community as well as the broader Python community, and how we might actually go about fixing it. So first, before we can dive into any of the details about this, I wanted to sort of formalize what I mean by the Zen of Python. It turns out that Python actually has done this for me. There's a little Easter egg in pretty much every Python interpreter that if you type import this, you'll actually get a nice readout from the Python interpreter telling you exactly what the Zen of Python is. It's a series of statements that enumerate, exactly what the principles are of writing Python code in order from sort of most important to the least important. So you read down this list and see what applies in your particular case. And so, I don't want you to read all these here. You can read them all offline. You can look at them later. But what I want you to think about is, we often encounter tension in the PyHPC community when it comes to writing code, which is, we often will make trade-offs against this list when it comes to getting high performance. And that's because, we actually know how to measure performance of Python code, and we do it very often. And we actually care because, we can't solve the problems that we're trying to solve unless we actually do get high performance. And so, it's sort of a fundamental part of our community, but it often leads us to conflict with this Zen of Python. And so here I've hinted at just a few of what those things are. We compromise all the time. In particular, we often, I'm sure, compromise on the beauty of the code that we write as well as the readability and so forth. So why does this matter? Well, today the PyHPC community is really a much smaller subset of the broader Python community. But I don't think that that's going to be true for very much longer. And the reason for this is that there are a lot of Python users out there today who are encountering high-performance computing problems. Right? They're encountering big data problems, deep learning, machine learning, even modeling and simulation codes. Right? These are starting to expand beyond what is traditionally the supercomputing universe. Right? The more normal Python users are starting to have these problems. And so I think it's important for us as a community to actually endeavor to actually engage with this class of users. And in order to do that, I think we have to write code that is more Pythonic, but without compromising the performance that we've been getting so far from our code. And so we as a community, I believe, should really be trying to, not just provide tools to solve such HPC problems in Python, but also to, make it possible to use those tools in the canonical Python way, the very Pythonic way. And so what I want to investigate in the rest of this talk is sort of what prevents us from doing that today, why we don't do it, and then how we might actually go about fixing that problem going forward. Okay, so let's start with an example of something that I'm particularly familiar with, which is building big simulation codes, and how we might write that in canonical Python to start today, just using sort of normal Python libraries and Python software. So let's say I want to do a big numerical simulation for a combustion simulation with both multiphysics and chemistry. The first thing I'm going to do is I'm going to start writing some NumPy code. I'll probably have 40 arrays for all my cells with all their XYZ coordinates and chemical species. I might have fluxes and 5D arrays and so forth. I'll be writing nice canonical NumPy code, this very Pythonic code, right, where you push all your looping into the library, and you just let all the NumPy handle all the loops for you. And it's incredibly simple to write such code. The simulation itself is complex, but the Python code itself is actually pretty beautiful. And whenever I've done this, I've very much enjoyed that process. Once I've done building my simulation, I'm probably going to have some in situ analyses, right? So I'll offload some code onto pandas to do some statistical analysis, maybe some group bys over chemical species and so forth. I might turn around and pass some of that data back for doing things like uncertainty quantification, for perturbing the simulation, see how stable it is. I'll pass some of that data over to matplotlib so I can make plots to see what's going on inside of my simulation. I'll pass some data over to, maybe another thing I'll do is I'll pass some of my simulation data over to scikit-learn. I'll build like a support vector machine for having a classifier that recognizes like the flame wavefronts inside of my simulation. And then I'll pass that over to like a VTK, the visualization toolkit, to actually render it so I can see it, see what's actually going on. And of course, I could even like pass some of this data back and forth between matplotlib and VTK and so forth. And really, this is actually very elegant. Anytime I've built code like this, it's really been enjoyable to me, and I've really enjoyed doing it. It's very high productivity, and I get code that works, and I can manipulate it and change it and try experiments and try new ideas very, very easily. It's really quite beautiful, and in that sense, it's very easy to build such programs in Python, which is why I love it. And I think this really speaks to Python's strengths, right? This ability to have these composable libraries where you sort of glue them together, you can pass data types back and forth is really important to the success of Python as a whole, right? This is why so many people use Python and prototype things in Python so efficiently, and they love the productivity they get. There's a few important properties I want to call out here that makes Python successful in doing this. First, we have dynamic typing with late binding. It means that we can pass these whole objects between libraries with no knowledge of data representation. Second, we have a global namespace for passing objects between these libraries. We don't have to worry about, pointers and other sorts of nasty details. We just pass these objects and they all live in the same namespace. And third, this whole program has sequential semantics. And what that means is it looks sequential, even though there is some parallelism in here, right? Oftentimes NumPy is accelerated with OpenMP and vectorization. Scikit-learn and VTK and scikit-learn has the same thing. VTK has a graphics pipeline backing it, right, which has a lot of implicit parallelism in it. But at the Python level, I just see sequential code. That makes it really easy to reason about what's going on and makes it really easy to think about, the code that I'm actually writing. And this, these things are really core to Python's success. I mean, there's other things that make Python successful, but I think this is one of the most fundamental things that makes Python successful and why people love using it. And it really is what, in my mind, defines the essence of having Pythonic code. Okay, so let's look at how this breaks down when we try to do high-performance computing with Python today. So let's say I'm going to take my simulation with all of the different phases and analyses here and try to run it on the Summit supercomputer. Well, the first thing that's going to have to happen is I'm going to have to run on multiple nodes. So I'm going to need multiple processes. So I need some sort of communication library to help me do that, right? And the first thing, that pretty much all of us reach for is something like MPI for Pi, which is going to allow us to sort of embed the MPI programming model and communication layer inside of Python. And the first thing that does is it means we have to run, different number of processes for each of these different phases on different numbers of nodes, right? So the simulation is going to run on n nodes. My analyses are probably going to run m nodes where m is smaller than n because, I'm going to slice the data a different way. And then, my visualizations all run on one node because I'm either making plots or rendering to a graphics context that I need to reason about. And so what that means is that, effectively to interoperate here, I have to read and write data to and from disk between these things because I can't, hook up communication in different ways between these different sets of nodes very, very easily, right? And so I read and write files to disks, and I have 3 separate programs now for dealing with each of these different phases. And I end up being IO bound between these two things, between these different phases. And of course, this also destroys my ability to do uncertainty quantification because now I can't pass in situ data back in memory. I'd have to do it through the file system, which would be incredibly slow and slow down my simulation way too much. Additionally, I'm going to have to, get rid of my nice, pretty NumPy code here. I'm going to have explicit Go cells now that I'm going to have to manage when I actually pass data between the different chunks, and so I'm going to have to worry about that. I'll probably replace NumPy with CuPy to target the GPUs on Summit, but that comes with its own trade-offs. If I want to target all the GPUs and use NVLink between them, I'm going to run with 1 process per node, but then I'm not using CuPy's drop-in replacement for NumPy. I'm writing much lower level code to do communication between those GPUs explicitly. Alternatively, I could run with 1 process per GPU, and then I get the drop-in CuPy replacement for NumPy. But then MPI for Pi has no knowledge of GPU direct, so I get no communication via NVLink, which makes me sad. So if you step back and look at this slide as a whole, you can see there's all sorts of exceptions and changes that we make to our code today in order to actually run at scale and actually do these kinds of computations on supercomputers or in the cloud and it really messes with the Pythonic nature of the code that we like to write. Right, effectively, it breaks down a lot of the things that we do that we would like to see, in order for making our Python code Pythonic. And that's great. That's actually not a bad thing for us, right? We as the community know how to solve these problems, and really we're looking to get our work done. And I think it's important that we do that. We can't just have the ideal solution in all cases. And so it's not necessarily a bad thing that this is the case, but it means that, effectively we're limiting the scope of our work then and our solutions that we develop to people who are like us, right? Effectively people who can, understand these kinds of programming models and problems and hardware and software and put them together. It just happens that our code is embedded in Python. It's not really Pythonic in a way that, an outside Python user could look at it and say, oh, I can actually understand what's going on here. And so I think, you shouldn't look at this as like a necessarily a bad thing. It's more like a stepping stone, but I think we should endeavor for something more. Okay, so what are the challenges that we're facing? And I really think there are two categories of challenges we need to address here. First is heterogeneity and scalability, and the second is going to be composability overheads of composing these libraries on big supercomputers and in the cloud. So first, for heterogeneity and scalability, everyone in this audience, I'm sure, knows that both CPUs and GPUs are heterogeneous processors, and they're getting more and more heterogeneous. We have heterogeneity in our communication networks as well as our I/O devices, both in supercomputers in the clouds. Anecdotally, I've been getting tons of users telling me that their desktop workstations are no longer sufficient for solving their problems. They need at least in the order of 10 to 100 GPUs to solve a lot of their computational problems. And so, this problem is growing, and I think there's lots of users out there today in the broader Python community that are having high performance computing problems that we need to solve, with heterogeneity and with being able to scale. And second, when it comes to composing libraries, here's a cartoon example where library A produces a matrix, library B is going to consume it. And today, we have to convert types whenever we pass these objects between libraries. Whenever these libraries don't recognize an object's type, they do something like convert to NumPy, and then they may be converted again into their internal type. So you're making at least one, if not two copies in the process of doing this, which is really inefficient, from a high performance computing standpoint. Additionally, when you think about partitioning for distributed execution, right, these library calls may want to have different partitions, right? Library A may want to produce this matrix in row partitions, and library B may want to consume it with a tiled partition. And so you need some way of reasoning about, the coherence of this data and these partitions between when you pass this object from library A to library B. So two observations, these challenges exacerbate each other. For example, the partitioning problem making this, interoperability problem harder between the two libraries. And the second observation, these challenges get worse over time, right? Effectively, we're going to have more heterogeneous and larger machines that we're going to have to tackle even in the future. And we're going to have more libraries that need to compose with each other going forward in more interesting ways that maybe we can't even think about today. And so I really think that we should endeavor to really think about this problem now and attempt to address it so that we don't get stuck in a place where we're not going to be able to solve it in the future. Okay, let's break these challenges into a little more detail so we can actually go about tackling them. So first, I think it's worth pointing out that we're actually grappling with this heterogeneity and scalability crisis today. And you see it in the form of many, many new programming models being embedded into Python. So for example, like we have communication libraries embedded into Python now. We have task-based libraries embedded into Python for doing tasking. We have internode parallelism models for targeting CPUs and GPUs. And we have deep learning libraries for targeting, deep learning on lots of different kinds of machines. And all of these, embed new programming models into Python. And I think, the takeaway that you should take from this slide is that things are not really, a lot of these libraries are not really Pythonic. And they're not Pythonic for a few reasons. One is most of them don't let you write beautiful code. Maybe some of the deep learning libraries do just for their particular domain. But a lot of these other things, the code is not always necessarily beautiful. Second, not many of these libraries let you write simple code, right, as defined by the Zen of Python. Right, and so it would be very difficult for a lot of outside users who don't understand explicit parallelism and so forth to come in and look at our code and understand what's going on. Third, not many of these libraries naturally compose with each other. It's often very hard to get these different libraries to work together. You have to do a lot of finagling with the code, and that's not really Pythonic. You should just be able to glue Python libraries together and have them work. And so finally, if you brought in an outside observer and looked at the code that we write with these libraries, I don't think anyone would say that it's Pythonic. It works, and it's very, very efficient at getting good performance. And we can prototype much more naturally in Python, but it's not necessarily Pythonic in my opinion. And I'm sure there are people who are going to quibble with me about this, but I think at least if you go back and look at that Zen of Python and look at the spirit of it, and you look at our code, it doesn't always align with that Zen of Python. And for the second challenge, the composability overheads, you can see the community grappling with this in the invention of Apache Arrow. So Apache Arrow, for those that aren't familiar, I borrowed some of their slideware here. Effectively, what it allows you to do is to solve this interoperability problem inside of a single node. So you have a bunch of libraries at the top here, a bunch of file formats at the bottom. Wherever you would pass things, you'd have to copy and convert all over the place. What Apache Arrow does is it gives you an interface for all these different things to interoperate. So effectively, they know that they have the same interface between these objects for looking for like memory layouts and so forth. And that way you don't have to do the copies and converts whenever you pass things between them. In particular, it does this for pretty much lots of different kinds of data types, especially effectively anything that can map into a data frame is something that Apache Arrow can represent and help you reason about the memory layout and so forth. And this is great. It actually helps us solve the single node interoperability problem. But I think when it comes to PyHPC, we actually are going to have some variations on this problem that it's not going to solve. And I'm going to talk about this more later, and we'll dive into the details of why that's the case. Okay, so what is the way forward? How do we actually engage with these users beyond our community who actually need to solve high-performance computing problems with Python, but don't have the expertise that we have in this community? I think the only solution for reaching this class of users is to provide drop-in replacements for popular Python libraries. So what I mean is you actually change just this one import statement at the top of your program, and then you should be able to run your code on lots of different kinds of machines. Everything from your desktop workstation out to things like DGX SuperPods in the cloud or the Summit supercomputer. And I think it's really important that we do this. Like effectively anything more where they have to change code or rewrite code is going to be really, really complicated and difficult for these users to grasp. And drop-in replacements are not a new idea. I'm hardly the first one to suggest them. NumPy has lots of drop-in replacements out there. So for example, there's CuPy and Boreum that give you a single GPU drop-in replacement. More recently, Leagate NumPy gives you multi-node, multi-GPU drop-in replacement for NumPy. Pandas also has drop-in replacements. So there's things like cuDF for a single GPU. There's Modin for multi-node, multi-CPU drop-in replacement, and Leagate Pandas, which is multi-node, multi-GPU. And I think when it comes down to these drop-in replacements, the other important reason to have them is that there's lots of code built on top of these libraries that assumes these interfaces. And if you try to change those interfaces, then all that higher level code breaks, right? And so it's really important that you have these drop-in replacements that don't break software composability. And the other part of this is that really these users are not particularly sophisticated, right? They're not going to have expertise in parallel programming and high performance computing. And so this is really the only class of changes that we can really provide and ask them to do that they're going to understand and be able to grok in order to target the kinds of machines that they really do need to access in order to solve their problems. Okay, so it's easy enough to say that drop-in replacements are the solution for reaching these kinds of users and that we should just all go off and do them and that's the end of the story. But that can't be the end of the story because it's incredibly hard to build drop-in replacements, especially ones that target, lots of different scales and heterogeneity of machines. So just to enumerate what why this is hard, first, these drop-in replacement library developers are getting crushed on all sides with complexity. So first, you're getting complexity from the library itself, like its API. Pandas in particular, I'm picking on here because it's notoriously complex. It has a library API that's, very nuanced and has lots of idiosyncrasies to it that are really hard to understand and get right. And so you're dealing with complexity from that side. You're also dealing with complexity from the hardware itself, right? You have lots of different classes of machines you need to run on. You're getting complexity from, adjacent libraries that you have to interoperate with. So you have to deal with all the interactions with, in this particular case for Pandas, might have to interoperate with NumPy and scikit-learn and so forth. And so this library developer here is now, they're really getting crushed by complexity from all sides. And so we can't just say drop-in replacements are a solution because that creates what I think is an untractable problem for these library developers to solve. We actually need to provide a secondary solution to actually help them build these drop-in replacement libraries and do so in a way that enables these libraries to interoperate with each other. So how can we alleviate this complexity? Well, unfortunately, there's nothing we can do to relieve the complexity of the library API. And the reason for that is, it has to stay the same. And, whatever, it's effectively a standard that the Python community has agreed on, that this is the semantics of this library, and we can't really change it, or we're going to break other people's software. That being said, I think we can solve these other problems, right? So we should be able to solve the interaction with other libraries. This is effectively what Arrow is doing today for single node. But we're going to have to make some changes, I think, to actually tackle that for multi-node. And we should also be able to do something about this, solving, addressing some of the portability problems of making sure that the code that the drop-in replacement library developer produces is going to be able to run on lots of different kinds and scales of machines. We should be able to fix that as well. Okay, before I describe what I think the solution to this problem is, it's worth asking first, why isn't Apache Arrow the solution? Before we go on and propose something new, let's at least examine why what's out there today is not the right thing to solve this problem. And my disclaimer to this slide is that nobody should take this as a critique that Apache Arrow is bad. Apache Arrow is very good at solving the problem it was designed to solve. It's just not solving the problem that we needed to solve in the PyHPC community. So Apache Arrow provides this data layout interface for a single allocation of data, which is great when you're inside of a single process with a single Python interpreter. But if you've got multiple nodes, multiple Python processors, or multiple Python interpreters and different processes with partitioned data across all of these different interpreters and different processes, this is no longer the right interface at which to think about composability. You want to think about a higher level interface that actually encapsulates all the data across all of your processes and interpreters, and not just across your one interpreter living on a single node. Because effectively what you need to do is manage the interoperability of those partitions that the different libraries are going to expect of the same piece of data. On the compute side, Apache Arrow has a very limited execution model. It's kind of like an RPC-based thing. They also have some support for doing offloading to GPUs. But they punt on problems like managing parallelism and synchronization. They make that the user's problem. And they also don't help with problems that we all, sort of are natural problems to those of us in the HPC community, such as like trying to hide communication latency with computation, right? There's nothing that automatically helps you do that in Apache Arrow. And I think, to make these the drop-in replacement library developers' life simple, you really need to provide an interface that's going to help aid that process for those library developers. Okay, so the solution I'm going to propose is actually not a new one. It's just going to be a twist on one that existed for a very long time until quite recently and was incredibly powerful and sort of proved itself as a good solution. And I'm just going to twist it slightly and apply it in a different context. So, one of the great sort of features of computing over the 20th century and into the early 21st century was this modern out-of-order processor. Right? Effectively, what it allowed us to do is have library developers that sat on top of a sequential instruction set architecture. They built their libraries. Users hook together their libraries in very sequential nature, right? You can call function foo from library A, bar from library B, baz from library C. The compiler compiles this into a bunch of assembly code in the same program order that it was specified in the program. And then you have this modern out-of-order processor that effectively performed magic, right? It would do things like extract instruction level parallelism across library boundaries, grab instructions from bar and hoist them up into foo in order to hide memory latency from foo's loads and stores. It would, do all that overlapping for you. It would automatically manage the coherence of your caches, right? So that you would move data up and down the hierarchy. You didn't have to think about that when you're the library developer. And it would do all this dynamically to react to things like data-dependent behavior and, branches and all sorts of things. And this, was how we built composable software, for a very, very long time, right up until the end of Dennard scaling, which forced the multi-core revolution. And so, this is a proven technology for building composable software. And what I'm going to propose here is that, even though this died for sort of single node cases, I think there's actually a chance to do something similar in software at the scale of high performance computing that we care about in this community. So what if we did the same thing to target something like the Summit supercomputer? So I'm going to build sort of an analogy here in this block diagram. So this is the same block diagram as on the left, but I'm going to change some of the names now to reflect, maybe having a processor that actually tries to target a full supercomputer instead of just like, the ALUs and local processors inside of a single node. So instead of having, maybe we have a latency queue of work that's going to target the CPUs across the supercomputer. Maybe we have a throughput queue that's going to target computations of the GPUs. Maybe we have a data movement queue that's going to target the NICs. And maybe we have like an object store for each Python interpreter that's going to store the local data living inside of that Python interpreter. And now what we're going to do is we're going to have our program that's going to, we're going to have a program that's going to sit on top of an API that's going to actually try to target this supercomputer. And I'm going to describe this, I'm going to describe both, the design of this distributed execution engine, as well as an interface that our library developers who are building drop-in replacement libraries should be able to sit on top of. That is then going to be able to make it easy for them to develop their libraries and target a supercomputer to actually run on. So first we need an analogy here. We're going to coarsen up some of the analogy from the modern out-of-order processor. So instead of having instructions, we're going to have tasks. We're just going to be coarse computations that are going to run on a CPU or a GPU, maybe say a few hundred microseconds or a few milliseconds. And then we're going to have, instead of having registers, we're going to have chunks of data that are going to be operated on by these tasks for doing actually our data dependence analysis. And once we have this analogy, and I'm going to describe the sequential execution API that implements this analogy on the next slide, what we can do is we should be able to automate all the things that we need to target this supercomputer. We can automatically extract task-level parallelism across library boundaries that should allow us to hide memory latency by automatically overlapping computation with communication. We should be able to automatically manage the coherence of data in this memory hierarchy and do all this dynamically to react to things like dynamic behavior in Python code. And so this should really be the powerful, platform on which our library developers who are building distributed or who are building drop-in replacement libraries can sit, so they don't have to suffer through the amount of complexity that they were in that the initial diagram that we presented. So let's see how they actually offload this complexity, right? We still have our complex library API that they have to deal with. We can't help them there. But now they should be able to offload complexity of data representation onto this distributed execution engine API. So let's just propose a potential data model here. Let's say we use data frames, just like Apache Arrow, since that seems to be very popular and something the community can already agree on. So the library developer will map their data types into data frame-like objects. But instead of having a memory allocation and layout, what this will do is this will actually be sort of a conceptual data frame, which may actually be partitioned into sub-pieces that actually live in different parts of the machine, right? And so we can actually partition this in different ways. We can chop up the rows and columns of this data frame and describe different subsets of it. And then our distributed execution engine is going to maintain the coherence of this. So, effectively, you should be able to see whenever you do a read of any subset, you'll see the most recent writes to that subset from whoever did those writes. That's what I mean by maintaining coherence. Similarly, for computation, we can offload that from directly onto our distributed execution engine. So each API call is going to turn into one or more task launches to actually, run this particular computation. Right, so something simple like NumPy add will turn into like one task launch that's going to read and write, a couple of arrays. But similarly, like pandas.join will probably launch a few different tasks, right, to actually do that join computation and operate on different columns and of that data frame, of those data frames. Right, so the library developer will just maintain this mapping. And notice that this is going to allow us to actually give us our portability across lots of scales of machines, right? So we can actually have, we can later specify whether these tasks are just abstract computations. They don't say whether they're going to run on a CPU or GPU yet. We might bind them in different ways, do the late binding trick that we do in Python all the time. We'll bind them to a CPU or GPU at a later point. But at the same time, we're just specifying, what this computation is in the library implementation. We have to think about whether it's going to run on a CPU or GPU. So the same library code can actually run on lots of different scales of machines, or different heterogeneous machines. Tasks will naturally name their data frames or sub chunks of those data frames that they're going to operate on, those sub parts, right? That's the definition of a chunk. Effectively, a subpart, a subset of rows and columns that they're going to operate on for doing their execution. And that's what's going to allow us to automatically infer, where dependencies exist. So our execution engine will be able to maintain the sequential semantics or the appearance of it, but it's going to be able to reorder tasks to do things like hide memory latency as part of that process. So let's actually see how that works in practice in just two slides here. Okay, so first let's describe, this first class support for data partitioning in a little more detail. Effectively, when I talk about data partitioning, what I mean is that, we should effectively be able to make different views onto this data for different libraries to access, right? So coming back to our simulation example from earlier in the talk, right? We have two different libraries here, NumPy and Pandas, that are probably going to want different partitions of the cell data, right? So we might want to have a spatial decomposition for NumPy to use for minimizing surface to volume ratios for stencils. But then Pandas probably wants something like partitioning on the chemical species in order to do things like group bys efficiently and so forth. So we should be able to have different partitions of our data frames, and the library shouldn't have to think about it, right? Effectively, it should just be able to automatically, have the system be able to use whatever partition they want to use, and have the system automatically manage coherence for them. Importantly, these partitions need to be made dynamically, so that effectively you can create these on the fly to react to data-dependent behavior, and in both the Python code as well as the data itself. These partitions are just views, so effectively, if you write to one of these partitions, the next thing that reads it, even if it's in a different partition, even if that data exists in a different partition, it needs to be reflected, and that's what it means for the execution engine to maintain the coherence between those things. And just to contrast this with how things are done today in other programming systems like Dask and Ray, partitions in Dask and Ray are effectively collections of features that enumerate memory allocations in different nodes. Right, and if a library wants to change a view and make a new partition, they effectively need to make a new set of features and then do a swizzle set of copies to sort of shuffle all the data around between those different features. And this really hinders software composability because it means that libraries don't know about each other's partitions. They don't know how they interoperate, and they might have trouble recreating new views from previous ones. And so it's really hard to build composable software in such a way. And that's why having multiple partitions with coherence maintained by the execution engine is so important. And finally, we should have support for hierarchical partitioning of data, right? So if this is like our node partition for the cells, maybe we want to further partition, into smaller chunks for the GPUs inside of each node, right? And so we should be able to hierarchically partition our data in our API. Okay, so I promised you that we'd actually see how we can actually overlap computation with communication automatically. So let's say we have a Python program that looks like this. We've got a bunch of canonical Python libraries being called in this program. Each one is turning around and launching off one or more tasks to actually run their computation. That's what those dots are over on the right-hand side. This looks like a standard Python program, but instead the libraries are automatically targeting our distributed execution engine. Well, what our distributed execution engine is going to do, it's going to build a dependence graph by looking at what chunks of data each of those tasks are going to be using, subsets of the data frames. And then when you schedule that, you can actually automatically reorder things, consistent with the dependencies that existed in this graph in the middle here. Right, so as long as you maintain the dependencies in this graph, you're maintaining sequential semantics, but it gives you freedom to do things like reorder things. So you can hide latency of things like copies, or if you have sends and receives to remote nodes, you can do things like stick that NumPy computation between the send and the receive, so you can automatically overlap communication with computation. And notice that we effectively overlapped computation with communication with a computation that came from a different library than the one that was initially doing the send and receive. And that's really powerful because that means that you can find parallelism that you can actually hide latency in a way that no one would actually ever want to write by hand, right? This is how this is exactly how tuned HPC programs work in the real world, where you're hoisting code all around to stick it in between MPI sends and receives to actually overlap things. But instead of baking that into your code, we've had this nice, pretty Python program on the left that then executes like a tuned HPC program on the right. And that's a really powerful concept for library developers, because it means they don't have to think about this problem, right? They can offload that problem onto the distributed execution engine and just allow it to automatically take care of doing that overlapping for them. Now you might be asking is, how do we hide the dependence analysis latency here? Well, there's a very easy technique that effectively modern out-of-order processors pioneered, and all sorts of people have used since, including graphics pipelines, which is deferred execution, right? So effectively, instead of you make the tasks look like they're running eagerly, but instead you're kicking them off asynchronously, and they're sort of running ahead to actually kick off tasks in advance of where they're actually executing. So that allows us to create a pipeline, just like your modern out-of-order processor. We have a construction wavefront for kicking off new tasks. We have an analysis wavefront for where we're doing the dependence analysis. We have an execution wavefront where we're actually running tasks on the CPUs and the GPUs. And then we have a data movement window between these, which allows us to hide the latency of communication. And finally, we have a destruction wavefront, cleaning things up as we're done running things. And effectively, you can imagine that this is your pipeline from your out-of-order processor, except now we're operating at a much coarser scale and in software. And importantly, you can also think of like this. You notice that we never actually build the whole graph all at once. It's a sort of a sliding window, which is analogous to your reorder buffer in your modern out-of-order processor. And it's important to take away this is neither eager nor lazy execution. We're still going to run all of your computations no matter what, just like you would in an eager computation with normal Python. But it's not lazy execution the way DL libraries are, like TensorFlow and PyTorch, where they wait to build up the whole graph and then they optimize it and they execute it. Like, we're not doing that. We're just got our normal Python or normal pipeline of tasks that we're running, and we're hiding all the latency of doing analysis with that. Importantly, you should take away that this dependence graph is being built on the fly, right? We're doing all this at runtime, both because Python is dynamic. We don't know which tasks are going to be launched until runtime. It's really hard to do static analysis on Python code, so it's much better to do it dynamically. And that allows us to deal with things in Python like arbitrary control flow and so forth, and branches and all those kinds of problems. It's worth pointing out here that there are some open problems. I don't have a full solution for what a distributed execution engine looks like. Here's an example of something that remains to be solved. So if you look at the left side of this picture, I actually left open a step. Right. Effectively, these first two stages of this analysis here is a functional specification of the program. They're both defining what it means for the program to be correct. Right. Effectively saying this is the order of things have to be run in, and here's the dependence graph that has to be abided by to actually make the program correct. But over here on the left, we actually have a schedule, right? And that implies reasoning about performance. And so what we need is there's a step here which actually some sort of mapping or scheduling interface that's actually going to figure out how to schedule this graph onto the particular machine that you actually want to target. And there are lots of different ways you could imagine tackling this mapping scheduling interface problem. One is you might not even have an interface, right? You might have a magic scheduler that can always perfectly guess the right mapping onto CPUs and GPUs on the target machine. Right, but of course, I'm hesitant to do that just because it flies in the face of that Zen of Python that we saw at the very beginning, right? In the face of ambiguity, refuse the temptation to guess, right? And we don't want to be guessing wrong, certainly not. We want to have some way for users to help direct us when we don't necessarily do the right thing. So maybe we have an API to help them express placement or scheduling hints. So extend some of our library APIs to have hint arguments in some way. You can also imagine, Python library developers, those drop-in replacement developers annotating functions saying whether things prefer to be run on CPUs or GPUs. You can also imagine, a callback interface that allows you to dynamically pick, where things are going to be run based on the program that you're running and the state of the machine. I can imagine there are other solutions that I'm not even enumerating here that we might want to consider. But this is I don't want to suggest that, what I'm proposing here in this talk is a fully baked solution. In fact, it's far, far from that. There's lots of open problems and things that we would need to address and talk through, as a community to figure out how we want them to look. So with that, I want to conclude this talk by giving, a summary of the architecture that I think, is really important for us to reach communities beyond the PyHPC community. I think there are lots of people out there that have Python applications in the world today that need to run on the scale and heterogeneity of hardware down here at the bottom that all of us are using today. But they're not being able to use that, right? They can't access that technology and those speed ups and performance because they don't have the expertise. And the way to reach them is, of course, I'm proposing here is to provide drop-in replacements for very popular Python libraries to actually, make it possible for them to just change a few important import lines in their code and get access to these classes of hardware. And of course, in order to do that efficiently and to allow all those libraries to interoperate efficiently, I think it's really incumbent upon us to build some sort of API or some sort of execution engine, distributed execution engine that we'll be able to use to make the development of such drop-in replacements much, much easier, right? I think we have to make it ergonomic for ourselves or it's not even going to be tractable. The complexity will kill us. And so we need to have, solutions. And I think the idea of a distributed execution engine and its API is sort of, a natural way and a proven way, from past history with modern out-of-order processors as a way to tackle this kind of problem. Importantly, I don't think, we have to build this from scratch. I see a lot of the building blocks of the implementation of a distributed execution engine out there in the community today. I think, lots of systems have components of it. And I think it's a matter of us coming together as a community to try and sort of formalize what needs to be in this API to actually handle lots of different kinds of libraries on top of the API, as well as, thinking of different implementation strategies to actually make this a possibility. And so, this is what my research is working on today, right? The League project is trying to provide a proof of concept that you could build something like this in the future. I don't think we have all the answers. In fact, I know for certain that there are lots of things that we don't know. And there's lots of libraries that we haven't even considered. All we've looked at is NumPy and Pandas so far, which is, an interesting combination of libraries, but it's nowhere close to being, the full spectrum of libraries that we would want to consider for the construction of a distributed execution engine API. And so there's a long way to go. I think, I don't want anybody to take this as a call for standardization. In fact, I think we're probably years from that place. What I want people to take away is that, this is really something that we should start investigating now as a community because it's going to take a long time to build. And so really, I'm going to wrap up my talk here, not with a conclusion, but with a call to action. I think, we should go about trying to reprise the Zen of Python for HPC. we want to write more Pythonic code, both for ourselves as well as for people outside the community, so they can get access to all the tools and wonderful performance that we have access to today. And so we have 2 action items to do this. One is to build more drop-in replacements to reach people in the Python community outside of the PyHPC community. And of course, this is going to help those Python users that have HPC problems today. And second is to start, prototyping distributed execution engine APIs and implementations, just so that we can get a feel for what we think we want for building such drop-in replacement libraries. Because we have to make it easier for us to write Pythonic code too, in order to build these kinds of things. So with that, that's the end of the talk. We'll be having a Q&A session at the actual workshop itself. But if you have comments and questions offline, feel free to email me at mbauer@nvidia.com. I appreciate your time and attention for listening to this talk, and I hope you enjoyed it. Thank you very much.